This is video 4 from section 5.4, and we're now on part E, compute conditional probabilities using the general multiplication rule. Unless it's stated otherwise, we are to assume selection is done without replacement. In other words, it'll be a conditional probability. In example 1, it says, suppose you just received a shipment of 11 sets of headphones. 2 of the sets are defective. If 2 sets of headphones are randomly selected, one at a time, this is multi-stage, find the probabilities below round to 3 decimal places as needed. So let's make note of what we have here. We can determine the probability of a defective headphone because they said that 2 out of 11 are defective. So that's the probability defective. So then from that, using complements, we can figure out the probability not defective would be equal to 1 minus the probability defective, right? Which would be 1 minus 2 elevenths or 9 elevenths. Of course, you could probably do that without even going through that, but I want to make sure you remember how complements work, because the headphone is either defective or not defective. Those don't overlap, and that takes care of every headphone out of the 11. They're either defective or not defective. Okay, now that we have all this information, let's see what we are asked for. Find the probability that 2 randomly selected sets are not defective. In other words, both of them work. You reach in, you get one, and it's without replacement, and then you reach in and you get another one. So that, in other words, we want the probability that the first one is not defective. I'm just going to abbreviate that word. And on the second trial, the second one is not defective. So that's the multiplication rule in a multi-stage procedure. The and implies that. So when you go for the first, you reach in to get the first one out, there's 11 headphones there, and not defective, there are 9 headphones that are not defective. And means multiply. The next time you go to reach in there, we are doing this without replacement, so one headphone has been set aside, the first one. So now there are only 8 that are not defective, and there are only 10 sets of headphones left. Our answer is supposed to be rounded to 3 decimal places as needed. They don't ask for a fraction, so we'll just multiply this and get the decimal. 0.655. Okay. Find the probability that at least one of the two sets is defective. Recall, the probability of at least 1 is equal to 1 minus the probability of none. Because at least 1 would be 1 or 2 or 3, everything but 0. So we can use complements. This is the probability of 0. This is the probability of 1 is 2, 3, 4, all the way up to 11. So we'll use complements. That's the easiest way to get this. Okay? So that will be equal to 1 minus, now the probability that none of them are defective, right? In other words, let's say probability none of the 2 are defective. Neither one is defective. In other words, the first one's not defective and the second one's not defective. Well, that's what we just did here, right? None of the 2. In other words, 1 minus the probability not, just like we wrote before, defective, and then the second one, not defective. So we already have that. So that equals 1 minus 0.655 or 0.345. You can put the 0 in front if you want. You don't have to. We've seen that a bunch. Okay, So look at that one again. You're going to have problems like this, at least one. It's always 1 minus the probability of none. We're selecting 2, so that means the first one's not defective and the second one's not. None of them, none of the 2. And since we already calculated that, we could go straight to this calculation. Okay, in example 2, we have a jar with 33 yellow M&Ms, 12 green M&Ms, 20 orange M&Ms, 9 brown M&Ms. If 2 M&Ms are selected, find the probabilities below and round to 3 decimal places as needed. Okay, how many total M&Ms do we have? Let's see. 33 plus 12 plus 20 plus 9. 33 plus 12 plus 20 plus 9. What does that come out to be? 74 M&Ms total. Okay. We need that total, right? And probability, we're going to definitely need that total. Find the probability that both M&Ms are green. Okay. Would it be unusual for both to be green? Because it's saying if 2 are selected, so that's true for all these down here. If 2 are selected, what's the probability they're both green? Okay, so the probability that you reach in the first one's green and the second one's green. Okay, so the probability the first one's green, and this is conditional probability, so that means, remember they told us up here, without replacement. So the first one's green. How many greens are there? There are 12, and we just said there's 74 M&Ms total. But now we didn't put it back. Maybe we ate that M&M, and now there are only 11 greens and 73 total M&Ms. And we're supposed to find probabilities to 3 decimal places. This comes out to 0.024. But they ask us, would it be unusual for both to be green? What do you think? And we have to explain. Just an answer isn't good enough. We've got to explain. Well, yes. And why? Because, and this is easy enough to write, 0.024 is less than our guideline of 0.05. Anything less than or equal to 0.05 has any probability less than or equal to 0.05 is an unusual probability. So that would be unusual out of this big bowl of 74 M&Ms to get 2 greens, choosing one at a time and not putting one back, the first one back. Okay, find the probability that the first is green and the second is yellow. Green and yellow. Okay, first one green, we just saw that. That was 12 over 74, right? 12 greens, 74 M&Ms. Now, yellow. Okay, there's still, we just pulled the green one out, so there's still 33 yellows in there, right? They have not been removed. We've only taken out a green one. So we still have all the yellows, but we only have 73 M&Ms. So you multiply that, you get 0.073. All right, in C, we want to find the probability that the first M&M is yellow and the second is green. Okay, so let's change the order here. Now the first one is yellow and the second one is green. Let's see what that does. So when we reach in for a yellow, there's 33 yellows and 74 M&Ms. And then we reach in, the probability that now we draw a green, well, there's still 12 greens because we took out a yellow one. But there's only 73 M&Ms. So what do you think we get when we multiply those? Maybe you've already figured it out. We got the same answer. Well, notice when you multiply fractions, you just multiply numerator times numerator, denominators times denominator, if you were doing it like that, not just letting your calculator do everything. Well, you're still going to multiply 12 times 33 on the top. You're still going to multiply 74 times 73 on the bottom, right? So you should get the same answer. So it doesn't matter what order we pull them out, we still get the same answer. Okay, and finally in part D, It says find the probability that exactly one M&M is yellow and the other is green. Now it doesn't say what order, it just says after you've selected two M&Ms one at a time, you've ended up with a yellow and a green. So how would that happen? Well, it would happen if you got the green first and then the yellow. So this is the probability that you got the green first and then the yellow, or if you got the yellow first and then the green. Either way, you'd end up with exactly one yellow and one green. Well, remember, OR tells us to do what? Addition, right? And we already have the probability of green and then yellow, that's 0.073, and the probability of yellow and then green, and that's 0.073. So when we add those together, we get 0.146.